In this video, we're going to look at an example of a t-test where instead of samples being independent, they're dependent. So this may sound at first glance like it's bad data, that the observations are not independent, but that's not really the case. So for instance, it could be a sample, from a survey where we get data from the same individual time one and time two. So an individual's answer to the second poll is related to their answer in the first because, they're the same person. So let's do a sample problem here where we have a weight loss intervention. We have a diet program, and for our data, we have people weigh in at time one, then they go on the diet, and then after going on the diet at time two, we weigh them again. So here in this example, about 25 observations here at time one, time two. Our null hypothesis is that there's no change in average weight from the first time period to the second time period. Now here we can do a one-tailed test. So our alternative hypothesis is that the mean at time two is less than the mean at time one. Now, theoretically, we can justify this that if someone goes on a diet or weight loss program, unless it's designed completely backwards, as long as they stick to it, they should lose some weight. This is a relevant time to use a one-tailed test. Now, we're going to do this analysis. Let's go to the data and data analysis tab again. And we're going to select the t-test paired for two sample means. Now, unlike last time, we have some labels we can use since the data is in separate columns. So we can click that. Now, the variable one range will be the wait time before the wait time before intervention, including the label. And for variable two, wait time two after intervention, again, including the label because we checked the little label box. Okay, the hypothesized mean difference here would be 0. And again, we can leave that blank because that's the default here. I'll select to output the results in the same worksheet for ease, just so we can keep everything, easy to see and in the same thing, but you can choose any of these options. It doesn't particularly matter for the outcome. Then here are our results. Just expand that a little bit so you can read the columns. We'll interpret this the same way we would interpret a regular t-test that we did before. So here's the mean for the pre-intervention. At wait time one, the weight is 172 pounds on average. After the intervention, so at time two, it's down to 165 pounds. So we're moving in that direction that we had for our hypothesis, which is important when we're doing a one-tailed test. Now going down here, we have 24 degrees of freedom, which makes sense. We have 25 observations for each variable. The t statistic is 5.16. Since this is a one-tailed test, we'll focus on just the one tail this time. So the p-value is, let's slide that over so we can see. Here are the one-tailed tests. I'm going to highlight them just for ease. So the p-value is very, very small. You see the scientific notation. If we could turn that to number, very, very small. A lot of zeros there. This is way smaller than the p-value of 0.05. So we can reject the null hypothesis in favor of the alternative hypothesis. Basically what that means, we have enough evidence to conclude that the average weight loss among participants the average weight among participants is lower at time two than at time one. So it's successful in achieving weight loss. Now, if we're looking for trying to identify if there's an effect or not, we like small p-values. That means that there is an effect. So in practice, it means that we find evidence in favor of the alternative hypothesis. So first, you may be alarmed. This is a really small number, much smaller than the p-value of 0.05. So you may think something may be off, that it's so different from the alpha level. But that's not the case. The 0.05 is simply a cutoff. What this means is that if we pull up the normal distribution, we are way, way out on the right tail, which means we found a statistically significant effect. In fact, p-values can go even smaller than this. So instead of like 4 zeros here, you could have like 8 zeros if you had a lot of data and we're really finding a strong effect.